You ever wonder how you could walk through a huge sorted collection of data, like one piece at a time, without having to load the entire thing into memory first? Well, today, we're going to tackle a classic coding problem that does exactly that, the binary search tree iterator.
So picture this. You've got this tree of numbers, and it's all nicely organized. The real challenge isn't just hitting every number, it's doing it in perfect ascending order. And get this, you need to be able to stop at any point and just ask, okay, what's the very next number? How would you even begin to build something that could do that?
You know, the secret sauce to this whole thing is the data structure itself, a binary search tree, or a BST. It's got this beautiful built-in order. No matter which node you pick, you know for a fact that everything to its left is smaller and everything to its right is bigger. That one rule is what makes this whole sorted journey possible.
Okay, so let's make this official. We're not just taking a walk through a tree, we're actually building an iterator. Think of it like a remote control for our journey through the data, with a next button and a way to know when we're at the end.
So what are the rules of the road here? Well, we need to build a class, a BST iterator. It has to have two main jobs. First, a next function that hands us the next smallest number. Second, a hasANext function that tells us, hey, are we done yet? And here's the most important rule of all. The numbers have to come out in perfect ascending order. For a BST, that means we're doing what's called an in-order traversal.
All right, so how would you solve this? What's the most direct, kind of obvious way to do it? Well, the first thing that probably pops into your head is, let's just figure out the entire route before we even take a single step. We'll call this the full map approach.
The logic here is super straightforward. Step 1, we just do a full in-order traversal of the whole tree. Step 2, as we visit each node, we just dump its value into a plain old list or array. And finally, our next and hasNext functions, they basically just move a little pointer along that list we already built. Simple.
Let's actually see how this plays out. We'd start at the top, the root, and we just keep going left, left, left until we can't go left anymore. We grab that number. Then we backtrack up to its parent, grab that one, and then we check out its right side. We're just mechanically following that left root right recipe all the way through the tree.
And just like that, after that one big pass at the beginning, we're left with a perfectly sorted list of every single value from the tree. From this point on, our job is a piece of cake. Every time someone calls next, we just hand them the next item from the list and bump our pointer one step forward. It's clean, and it totally works.
So, we're done, right? This seems like a perfectly fine solution. I mean, it works, it's pretty easy to wrap your head around. What could possibly be the catch? Feels like we nailed it.
Well, you knew it was coming. There is a catch, and it's a really, really big one, especially when you start thinking about massive data sets. Our nice, simple solution has a major hidden cost.
And there it is. This is the twist, the follow-up question that just changes the entire game. It's not just about getting the right answer anymore. Now we have to do it using memory that's proportional to the height of the tree, not the total number of nodes. All of a sudden, our simple solution is just not good enough.
So what's the big deal? What's O of n versus O of h? Well, O of n memory, that's our first approach, means that if your tree has 1,000,000 nodes, you have to create an array with 1,000,000 spots. O of h memory, on the other hand, means you only ever need to store a handful of nodes at a time, just enough to find your way. For a big, balanced tree, the height h is way, way, way smaller than the total number of nodes n.
And this is where the problem really becomes crystal clear. Our full map approach is O of n, but the requirement is O of h. This isn't just a small optimization, we're talking about a fundamental difference in scale. Our simple solution would completely crash and burn if the tree had billions of nodes, but an O of h solution would handle it without even breaking a sweat.
So how in the world do we achieve this? We need a much smarter way to do this. Instead of creating a full map of the journey, we're just going to figure out the very next step, and we'll only do it right when we need to. Let's call this the smart stack approach.
The whole idea here is to stop thinking about a complete map. Instead, think of it like leaving a trail of breadcrumbs. We don't need the whole sorted list at once. We only ever need to find the single next smallest number. And we're going to use a classic data structure, a stack, to keep track of that breadcrumb trail for us.
Okay, so when we first set up our iterator, we don't look at the whole tree. Not even close. We just start at the root and go left. And we keep going left, pushing every node we see onto our stack. We only stop when we hit the very bottom left. At that exact moment, the node at the top of our stack is guaranteed to be the smallest element in the entire tree.
So the first time someone calls next, it's super easy. We just pop that top node off the stack. There's our answer.
But before we return it, we do one quick, crucial check. Does this node have a right child? In this case, nope. So we're done. We return the value, and now its parent is sitting at the top of the stack, just waiting for its turn.
And here's the magic. This is the genius part. The next time we call next, we pop the next value off the stack, but then we ask that same critical question. Does this node have a right child? Ah, this time it does. We can't just forget about that whole branch. So we jump over to that right child, and we immediately repeat the process from step 1. We go all the way down its leftmost path, pushing everything onto the stack. This basically reprimes the stack so it's ready to give us the next smallest number. We only do this little bit of work just in time, right after we've served up the previous value.
So there we have it. 2 totally different ways of looking at the same problem. One does all the work up front. The other does it little by little, only when it has to. Let's put them head to head.
This table pretty much tells the whole story, doesn't it? For space, the smart stack wins, hands down. O of n versus O of n is a massive difference. For the initial setup time, it's also way faster. The only thing the full map has going for it is that its next call is guaranteed to be instant. The smart stack is usually instant, but every now and then it has to do that little bit of work to find the next path. But on average, it evens out to be just as fast. It's a tiny price to pay for those massive memory savings.
Now, this isn't just some clever trick for one coding problem. This whole contrast reveals a really fundamental and powerful idea in computer science.
See, our first approach, the full map, is what you'd call eager computation. It does all the thinking, all the work right at the start. Our second approach, the smart stack, that's lazy computation. It puts off any and all work until the absolute last second, right when you actually ask for the answer. One is simple but can be incredibly expensive. The other is a bit more complex but way more efficient.
So the bottom line is this. The true beauty of that lazy smart stack approach is its efficiency. It never wastes a single brain cycle computing something that you might not even end up needing. It does just enough work, just in time, to answer the question you're asking right now, and nothing more. And this really brings us to the final big idea. This trade-off, this choice between being eager or being lazy, it's everywhere. It's in how your videos stream, how massive databases work, how apps on your phone load data. And it leaves us with this really critical question we have to ask in our modern world. When is it better to do all the work now? And when is it smarter to wait